Hello everyone, today we're going to discuss ionic bond versus covalent bond.
Scientists were just beginning to discover the anatomy of the atom. Now they wanted to understand its behavior, specifically the mechanism that enabled the atoms of certain elements to combine with the atoms of other elements to form new substances. In the early 1990s, compounds that have shaped the face of modern life. Our next great discovery started in the 1890s with the discovery of an unknown radiation called X-rays. It caused a sensation, and scientists immediately began looking for other substances that emitted strange, perhaps valuable forms of radiation. Over the next several decades, a number of scientists investigated the phenomena and together ended up shedding light on one of the great scientific sleuthing episodes of modern science. French physicist Henri Becquerel made the first significant breakthrough. In 1896, he conducted a series of experiments to see if various minerals emitted radiation. One of the minerals he happened to test was uranium. Becquerel's technique was to place different objects on top of an unexposed photographic plate, still wrapped in protective black paper. He would sprinkle the uranium onto another piece of black paper, then enclose the object between the uranium and the photographic plate. Later, Becquerel would develop the plate, and without fail, a ghostly photographic outline of the object would appear. From these experiments, Becquerel was able to prove conclusively that he had found a source for the mysterious radioactive rays that everyone was looking for. That source was uranium. From Becquerel, the investigation of radioactivity was taken up by Marie Curie. Curie and her husband Pierre undertook the job of isolating whatever elements were responsible for the radioactivity in uranium ore. For 2 years, the Curies boiled, sifted, filtered, and processed several tons of uranium ore. Finally, they succeeded in isolating 2 new elements contained in the ore, which they called polonium and radium. Marie Curie concluded that radium was 1,000,000 times more radioactive than uranium. More importantly, she determined that the mysterious form of energy which enabled radioactivity to penetrate other materials was not the result of a chemical process, but seemed to be atomic in nature. Unfortunately, her discoveries came at great cost. The dangers of being exposed to radioactivity were still unknown at the time, and in 1934, Marie Curie died of leukemia, believed to have been caused by radiation poisoning. Even the notebooks that she used to record her observations are still considered too radioactive to handle. It was the atomic nature of radioactivity that eventually attracted the interest of physicist Ernest Rutherford, whom we already met in the discovery of the electron. Rutherford found that radioactive material goes through a natural process of decay. As it moves through the process, the radioactivity spontaneously emits unstable and highly charged energy particles with the power to penetrate matter. Rutherford called them alpha and beta particles and gamma rays. Since those discoveries, we've learned a lot about radioactivity, the dangers as well as the benefits. Radioactivity has given us medical imaging, a treatment for tumors, a method for calculating the age of the Earth, and a power source for our spacecraft to explore the solar system. Even some smoke detectors contain a small amount of radioactive material called americium, which helps create a steady electrical current. When smoke particles disrupt that current, it triggers the alarm.
Well, bonding is that in 1916, the American chemist Gilbert Newton Lewis proposed that elements react to obtain the electron configuration of the inert gases. And this hypothesis is summarized in the Lewis octet rule for second period atoms, that atoms tend to combine and form bonds by transferring or sharing electrons through each atom, which contains 8 electrons in its valence shell. Note that hydrogen requires only 2 electrons to complete its valence shell because it has only a 1s orbital. Let's take a look on what is a valence electrons first. Now, the valence electrons are the outermost electrons in an atom, and the electrons in the highest occupied energy level, and these valence electrons participate in chemical reactions, and we can determine its chemical properties of a certain atom. Now you can see that in this figure that the electron dot structure are the diagram that show the valence electrons represented by dots. As you have here example in group 6A, there are 6 valence electrons represented by the electron configuration 1s2, 2s2, and 2p6, and these 6 dots represents the valence electrons of a certain atom. And remember that the outer shell or the valence electrons is also can be determined by on which group does a certain element or a certain atom belong. Just like for example, group 1 just like for helium, lithium, and so on and so forth. Group 2 for beryllium, group 3 for boron, 4 for carbon, 5 for nitrogen, 6 for oxygen, 7 for fluorine, and 8 for helium, or these are the noble gases. Now, let's take a look on what are ions. Well, an ion is a charged atom formed by the gain or loss of negatively charged electrons. We have to remember that when we are referring to a loss of electron or electrons, there is the formation of a positive ion, which we refer to as cation, and the gain of an electron or electrons produces or resulted to a negative ion, or which we refer to as an ion. Now, in this figure, let's take a look at the figure. We have here the sodium atom. Now, the sodium atom has 11 protons and 11 electrons. Now, we have made mention that in the formation of cation, there is a need or there is the loss of electrons. Now, if you could notice that there is now the formation of a positive ion or sodium as the positive ion, that the 11 electrons becomes 10. This means that there is positive 1 net charge in the atom. What about in the formation of an ion? Remember that it is the gain of electron. Let's take a look at the fluorine atom with 9 protons and 9 electrons, and there is an empty space there, that as to the octet rule, that there is a need to fill in or to gain an electron to complete the valence shell. And with this, the negative ion or negative 1 net charge is being produced in order to fill the valence shell, resulting to 10 electrons. Now, what is an octet rule? Since we have made mention a while ago, when we are referring to octet rule, an atom's gain or lost electrons to achieve a complete valence shell, and this is represented by the noble gases. Remember that noble gases is categorized under group A, While noble gases are stable, or these are inert gases sometimes, and generally non-reactive due to high ionization energies and low electron affinities. And that's according to J. and Lewis that we have to follow the rule of 8. Now, if you could notice here in this figure, the metals lost electrons to achieve a noble gas configuration, and a non-metals, which can be found at the left portion of your periodic table, that's the opposite of the metals, gain electrons in order to achieve a noble gases configuration. Okay, we have also here, class, the isoelectric, or the iso, which means equal or the same number of electrons. Just like, for example, we have the fluorine, the neon, and the sodium. All of these atoms, or all of these elements, contains the same number of electrons. That's equivalent to 10 because it follows the octet rule. And for example, in the case of fluorine has there is a need to gain 1 electron in order to satisfy the 8 electrons and to fill in the valence shell. If you could notice in the electron configuration 1s2, 2s2, 2p5, that represents 9 electrons for fluorines with the addition of 1 electrons or gain of electron. With a gain of electron, there is now the production of negatively charged ion, and that is an ion. And in the case of sodium is that 1 valence electron which needs to lose in order to produce a cation. And there's now, to follow the octet, there's a need to give the remaining 1 electron in order to have the equivalent 10 electrons. Okay? Kaya kung mapapansin nyo dito sa sodium is that in the first figure dito sa sodium part, you can see that merong isang electron at kailangan maalis yan, or it needs to be given. Kailangan niya ma-loss ito and para ma-follow niya ang tinatawag nating octet rule. And in the case of the neon now is already follows the octet rule with the 8 electrons surrounding the valence shell. Now, elements with the same family have similar valence and therefore similar ionic charge. Let's say in the case of group 1, or these are group 1, the alkali metals, group 2, the alkali earth metals, which represents the positively charged ion, or basically these are metals. And for group 3 to 8, there are elements which produces negatively charged ion. Okay, now let's proceed to ionic bond. Well, ionic bonds are formed between 2 or more atoms by the transfer of 1 or more electrons between atoms. And electron transfer produces negative ions, or we simply called as anions, and positive ions called cations. Ionic substances exist as crystalline solids. When the solid dissolves, the ions dissociate and can diffuse freely in the solution. It's like for the case in this figure, you can see here that electron is given away, since in the valence shell, in the last shell of this atom, there's a one spare of electron, and it has to be given away in order to satisfy the rule of 8. And you can see here that the other element or the other atom needs an electron to become stable. And how can this possibly be to become stable? There's a need to complete the 8 number or 8 electrons in the valence shell. Okay? Now, sodium chloride is an example of an ionic solid, or a sodium atom which has 11 protons and 11 electrons. It has a single valence electron in its 3s subshell. A chlorine atom, which has 17 protons and 17 electrons, has 7 valence electrons in its 3rd shell. And a chlorine atom, represented as 3s2 or 3s2 3p6. In forming an ionic bond, the sodium atom, which is electropositive, loses its valence electron to chlorine. And the resulting sodium ion has the same electron configuration as neon, that's 1s2, 2s2, 2p6, and it has a positive 1 charge because there are 11 protons in the nucleus but only 10 electrons around the nucleus of the ion. The chlorine atom, which is a high electronegativity, gains an electron. It is converted into a chlorine ion that has the same electron configuration as argon. That's 1s2, 2s2, 2p6, 3s2, 3p5. Now, the chloride ion has a negative 1 charge because there are 17 protons in the nucleus, but there are 18 electrons around the nucleus of the ion. You can see here in the formation of ionic bond that the sodium atom has to give the spare 1 electron to satisfy and in order for the chlorine atom to become stable. And since chlorine has a high electronegativity, it gains an electron which comes from the sodium. Okay? We have now the compound sodium chloride. Let's proceed to covalent bond. Covalent bonds are much more common in organic chemistry than ionic bonds. While a covalent bond consists of the simultaneous attraction of 2 nuclei for 1 or more pairs of electrons. The electrons located between the 2 nuclei are bonding electrons. Now, covalent bonds occur between identical atoms or between different atoms whose difference in electronegativity is insufficient to allow transfer of electrons to form ions. Now, covalent bonds form between 2 non-metal atoms with identical or relatively close electronegativity values. Take note, class, that covalent bonds is different from that of the ionic bond because ionic bond occurs between a metal and a non-metal, while covalent bond occurs between 2 non-metals, either identical or relatively one of the atom has high electronegativity values. And we will be determining how to look into the electronegativity values. A hydrogen molecule forms from 2 hydrogen atoms and each with 1 electron in a 1s orbital. The 2 hydrogen atoms are attracted to the same pair of electrons in the covalent bond, and the bond is represented either as a pair of dots or as a solid line. Each hydrogen atom acquires a helium-like electron configuration. This is the case of the 2 hydrogen atoms. Covalent bonds class has 2 types. We have the non-polar and polar bond, covalent bond. Now, covalent bonds are classified as non-polar or polar depending on the difference in the electronegativities of the atoms that are share the electrons. When we are talking about electronegativity, it is a measure of the ability of an atom to pull electrons towards itself. The electronegativities of some elements are presented that you can notice that there is an increasing electronegativity from left to right across a row of the periodic table, and there is a decreasing electronegativity from top to bottom or increasing from bottom to top of the columns or the group. Now, if the electronegativity difference between the bonded atom is less than 0.5, then the bond is a non-polar covalent bond. That is, the atoms share the bonding electrons equally, and the electrons represented by the bond are symmetrically distributed around each atom. An example of non-polar covalent bonds are just like the diatomic molecules such as the hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And also those polyatomic molecules such as the phosphorus and sulfur.
In ionic bonding, electrons are transferred from one element to another, and typically ionic bonds contain ions. In a covalent bond, electrons are shared. But let's go over ionic bonding first. Let's consider the reaction between an atom of sodium and an atom of chlorine. Sodium, as an atom, has 1 valence electron. If you look where it is in the periodic table, it's in the first column. It's in group 1A of the periodic table, and elements in that group all contain 1 valence electron. A valence electron is simply the electrons in the last or outermost energy level. Chlorine, which is a halogen, contains 7 valence electrons. It's in group 7A of the periodic table. The halogens are very reactive nonmetals, and the alkali metals, where sodium is found, are very reactive metals. Metals like to give away electrons, and so they form positively charged ions. Nonmetals, they like to receive electrons, and so they form negatively charged anions. So sodium is going to give chlorine one of its electron, or valence electron, since it only has one. So as sodium loses that one valence electron, it's going to acquire a positive charge. And as chlorine gains that electron, it acquires a negative charge. Now, going back to physics, if you have two like charges next to each other, what's going to happen? Like charges repel. They're going to feel an electric force that repels them or pushes them away from each other. But what's going to happen if you have a positive and a negative charge next to each other? These two are attracted to each other. They feel a force of attraction that pulls them together. And so that's what's happening between the sodium ion and the chloride ion. The sodium ion, which now has a net positive charge, is attracted to the chloride ion, which has a negative charge. And so these two, they feel a force of attraction. And that force of attraction, that electrostatic force, it binds them together. And so that creates the ionic bond. So keep this in mind. Within ionic bonds, you have a transfer of electrons, and the bonds that hold them are as a result of the electrostatic forces between opposite charges. Keep in mind, opposite charges attract each other. So now let's move on into covalent bonding. Let's look at hydrogen. A hydrogen atom has one valence electron, and it's in the first row of the periodic table. Elements in the first row, they want to have a total of 2 electrons in their outer energy level. Second row elements, they want to have 8 electrons. So elements like oxygen and fluorine, they want to satisfy their octet. They want to have 8 electrons. But hydrogen and helium, they can only have 2 electrons in their first shell. So each of these hydrogens, they need one more electron to fill that first shell with a total of 2 electrons. And both of these elements are the same. So what they're going to do is they're going to share their electrons. And so these two, they're going to form a bond. So when you see a bond, this bond represents the sharing of 2 electrons. And so this is a covalent bond. Anytime you have sharing of electrons, it's a covalent bond. Now there's 2 types of covalent bonds you need to be familiar with. Polar covalent bonds and non-polar covalent bonds. The bond between 2 hydrogen atoms is considered to be a non-polar covalent bond. The reason why it's non-polar is because the electrons are shared equally between those 2 hydrogen atoms. Now, if you look at the bond between hydrogen and fluorine, the elements are different. Fluorine is much more electronegative than hydrogen. Because fluorine is electronegative, it's going to pull the electrons toward itself. Now granted, the electrons are still being shared, but they're being shared unequally. And whenever you have an unequal sharing of electrons, you have a polar covalent bond, as opposed to a non-polar covalent bond. So because fluorine is more electronegative, as it pulls the electrons toward itself, fluorine is going to acquire a partial negative charge, and hydrogen is going to be partially positive. And whenever you have an object where one side is positive and the other side is negative, you have a dipole, you have a polarized object. And this is what it means to be polar. You have an unequal distribution of charge. One side is positive, one side is negative. So the electrons, they're not distributed evenly in that molecule. Is it ionic, polar covalent, or non-polar covalent? The first thing I would look for is to see if it's ionic. Typically, an ionic compound consists of a metal and a nonmetal. That's how you can easily identify it. Magnesium is a metal. Metals exist on the left side of the periodic table. Nonmetals exist on the right side. The nonmetals are on the upper right side, the metals are on the lower left side. So magnesium is a metal, and oxygen, which is on the upper right side of the periodic table, that's a nonmetal. So this is going to be ionic. Magnesium forms a +2 charge as an ion. It has 2 valence electrons. So in this bond, it's going to give away 2 electrons to oxygen. Oxygen, which is a chalcogen, magnesium is an alkaline earth metal. But oxygen, it has 6 valence electrons. It needs 2 more to get to 8. So once it acquires those 2 electrons, it's going to have a negative charge. As you can see, this compound is composed of ions. Now what about 2 chlorine atoms? Chlorine is a nonmetal. Whenever you have 2 nonmetals with the same type of element, it's always going to be a non-polar covalent. The electrons are shared equally because we have the same type of atom. Now what about sodium fluoride? Sodium is on the left side of the periodic table, so it's a metal. And fluorine is a halogen on the right side, so that's a nonmetal. So sodium fluoride contains ionic bonding. Now what about HBr? Is it polar covalent or non-polar covalent? Now the elements are different, so that could be an indication that it might be polar covalent. But you need to run a test. You need to calculate the difference in electronegativity. If the electronegativity difference is equal to or greater than 0.5, most textbooks they use this number. If it's 0.5 or more, then the bond is considered to be polar covalent. If it's less than 0.5, if it's 0.4 or less, then it's considered to be non-polar covalent. So if you need the electronegativity values, you can go to Google Images and type in electronegativity table, and you'll see some tables come up. Now I've seen different tables with different values. They don't vary much, but sometimes they do vary. So if you're doing a homework problem, use whatever table your book gives you. In the table that I use, hydrogen has an electronegativity value of 2.1. Bromine, it's about 2.8. And so the EN difference is 0.7. Therefore, this is going to be polar covalent. I'm going to write PC for polar covalent. Now what about iodine monobromide? What is the difference in electronegativity? Iodine has an electronegativity value of 2.5, and for bromine 2.8. So the EN difference is about 0.3, which means that it's relatively non-polar covalent. So I'm going to write NC. Again, make sure you use the table that your book provides, because if the values are slightly different, the result might be different. But the idea is that you want to find an EN difference of 0.5 or more to see if it's polar or not. So let's try some more examples. Determine if the following bonds is polar covalent, non-polar covalent, or ionic. So let's look at carbon and hydrogen. Carbon has an electronegativity value of 2.5, and for hydrogen is 2.1. So the EN difference is 0.4. For this one, I would commit this to memory. Anytime you see carbon and hydrogen, it's going to be nonpolar. This is a very common example that you'll see within chemistry and even organic chemistry. Now what about the OH bond? Whenever hydrogen is bonded to oxygen, nitrogen, or fluorine, you have a special case of bonding known as hydrogen bonds. Whenever you have hydrogen bonds, it's going to be polar, by the way. Oxygen has an electronegativity value of 3.5. So 3.5 minus 2.1, the difference is huge. So 1.4. This bond is very polar. So this is polar covalent. This is non-polar covalent. Now, if the two atoms are the same and they're both nonmetals, it's going to be non-polar covalent. You don't really need to do the calculation. Fluorine has an electronegativity value of 4.0. 4 minus 4 is 0, which is less than 0.5. Now, calcium sulfide. For this, you really don't need the electronegativity values. You just need to know that calcium is a metal and sulfur is a nonmetal. And then so you could say it's ionic. If you have one element all the way to the left side of the periodic table and another all the way to the right side, it's going to be ionic. So that is it for this video. Now you understand the difference between ionic and covalent bonding. So thanks for watching and have a great day.